Okay, welcome everybody. My name is Ricardo Vinuesa. I'm an associate professor at KTH in Stockholm. And today I'm going to tell you a bit about our work on using explainable deep learning to be able to identify coherent structures in turbulence. I would like to start by mentioning some previous works that have been looking at these questions. How do we define important regions in a turbulent flow, basically? And this is, of course, an important question from the perspective of control and sensing. So I need to know where these important regions are in order to know what I need to reproduce properly to predict the flow. But also at the same time, I need to be able to know what to control if I want to tackle the most fundamental mechanisms of turbulence. And this is a question that has been addressed first by Encina and Jimenez. This is a JFM paper this year where basically what they do is that they introduce perturbations in the flow and they evolve the governing equations, they integrate them numerically through DNS, and they basically analyze what of these structures are having a biggest impact on the flow, what of these perturbations and their structural typology has a biggest impact on the flow. And this is, of course, a method that is relying on simulations and is intrusive because when you are introducing a perturbation on the flow, you're actually modifying the flow, but they get very interesting results, essentially highlighting that strain-dominated vortex clusters are the most important regions in homogeneous isotropic turbulence, so in the case of a box, basically. So that's one approach to try to tackle this question of what are the most important regions on a turbulent flow. Of course, there's other approaches, and this is recent work by Lozano Duran and Arranz. They published that in Physical Review Research, and what they use is a methodology relying on causality and information theory. So in a nutshell, what they do is that they obtain a model decomposition of the flow, for instance through POD, although there are other possibilities. And then what you do is that you have time series associated with the coefficients that are connected with those modes. They remove the knowledge of one of these coefficients and they assess the impact of that coefficient on the future predictions of the rest of information in such a way that one can, in a quite objective manner, assess the relevance of the different coefficients to make predictions in the flow. So one can obtain this type of causality maps to really see which modes are affecting others, what are the causal relations among them. And this method relies on time series, is non-intrusive, which means that you're not modifying the flow, you are post-processing data, which is interesting from the perspective of analyzing the original flow without modification. And of course, it relies on having quite some access to data to be able to, have a good model decomposition, a good set of modes that can reproduce more or less effectively the original flow, and then the theoretical framework on which these information theory methods are relying is really sound. It's a very good theoretical framework. So if one has enough data, this is a very good way to go. What we propose here is an alternative which is based on explainable deep learning. So it's also non-intrusive in the sense that we are analyzing data in a post-processing step. We are not modifying the flow. And our approach has the advantage that it can be used in environments where less data is available. So if we are not able to have very converged PDFs or very good distributions of the temporal coefficients to be able to obtain those modes, for example, in the context of experiments where we might have lower resolution, then this method is still applicable. So that's the biggest strength of our explainable deep learning methodology. We're going to be using DNS data, a turbulent channel flow at Arita 125. This is a low Reynolds number channel, and the reason to choose such a low Reynolds number channel is to be able to have a lot of data. So we have 6,000 three-dimensional snapshots of the UV and W fluctuations. And what we're going to be doing first is identify intense Q events. The intense Q events, which were analyzed by Lozano Duran and others, are 3D regions that are segmenting the flow, and they basically satisfy this relationship over here. So what we are looking at is the instantaneous Reynolds shear stress, the instantaneous product of the U and V fluctuations, and we want this, the absolute value of this product to be larger than some hyperbolic hole threshold. So this is basically a number, a scalar, multiplied by the product of the URMS and the VRMS. And these terms, what they do is, of course, trying to scale the magnitude of the fluctuations with the wall normal direction. The channel is homogeneous in the stringwise and spanwise directions, but in the wall normal direction, each position basically has its own level of fluctuations, and what you do is that you use these U and V fluctuations to set the level over which you need to have something that is considered intense Reynolds shear stress, and this H is obtained through percolation analysis. So basically you look at a range of values of H and you pick the one that gives you the largest number of structures. A very small value of H will basically mean that everything is a structure, one big blob, essentially. And a very high value of H will be very restrictive, which means that you will have very, very few structures. In between, you will have a value where your number of structures is maximum. And that's basically what is typically used to set this hyperbolic hole number, again, as I say, with percolation analysis. So what we do is that we basically obtain these three-dimensional elements in the flow, the so-called Q events or intense Reynolds shear stress structures. And at the end of the day, this is just an extension to 3D of the classical quadrant analysis in 2D. Good, so let's look a little bit at our method. Our method is going to rely on an explainable deep learning framework. We're going to have 3 steps. In the first step, we are going to be using the three-dimensional U, V, and W fluctuations, so the current state of the flow, and with a deep learning model, we're going to predict a future state of the flow. So the U, V, and W fields in 3D in the future. And I will tell you more about what future and what type of models we're actually going to be using. Then what we do is that we segment the domain using the Q events. So we're going to identify these intense regions of Reynolds shear stress to identify three-dimensional volumes that we're going to consider our structures. And what we want to do is try to classify them by importance. So we want to see which of these Q events are in fact the most important. In the third step, what we will do is use the SHAP framework. SHAP is a game theoretic algorithm, basically Shapley additive explanations, which in a way is based on saliency methods. It really tries to see what elements of the input are more important to our output. So what it does in a nutshell is summarized here. I have my input flow field. I use my neural network to predict my future flow field. And then I go structure by structure, is these little vortices that are plotted here, and I remove them. And then I remove this structure, I repeat the prediction, and I see what was the effect of that structure on the error. So that's basically the idea. We want to go structure by structure and evaluate what is their impact on the error of our neural network. Okay. This is work led by Andrés Cremades. You can see here the reference is a preprint in arXiv, so you can really access the details there. And of course, as soon as the paper is published, we will release all the codes, so you will be able to reproduce all these results. At the moment, you can check out the details there. Now, which neural network are we using? Well, we use what is called a UNet, which you can see over here. A UNet is based on 3D convolutions, and the 3D convolutions, as I explained in previous videos, or 2D convolutions, are actually quite beneficial and quite important in the context of turbulent flows, because turbulence has quite localized information. This spatial information, which is associated with these coherent motions, can be effectively exploited by the convolutions to improve our predictions. So we actually use these convolutional layers where at the beginning I have simpler features being identified in our field, and through a concatenation of convolutions, I can hierarchically build more and more complex features that are in fact the elements that are being used for the predictions towards the end of our neural network. Our input is going to be 3 velocity fields in 3D, so the U, V, and W. And our output is going to be also 3 velocity fields of the 3 components, U, V, and W, in 3D. in a future step, so tip I plus 1. In fact, the time step between the input and the output is going to be 5 viscous times. So our input and our output are separated by 5 viscous units, which is, of course, a quantity characteristic of the near-wall dynamics. We also apply this framework to a range of delta t plus values from 1 to 5 viscous times, and the results are robust. So we obtain basically the same results that I will be describing in the next minutes for any delta t plus from 1 to 5. An important thing about the unit, which you can see here, okay, this is the architecture that we have. Our input is on this side, which are 3 channels, which are 3-dimensional. I apply several convolutions, and at this point, what I do is that I do a max pooling in such a way that I reduce the dimension of our data. I apply more convolutions, and then I get another max pooling to reduce the dimensions of the data. Then over here, I apply some more convolutions. I upsample to recover some size of the data, more convolutions, and I upsample again in such a way that our output will be of the correct size. So this architecture is called a U-net because of this shape of a U that you can see here. So this shape is giving us some data with the full resolution, some data with coarser and with progressively coarser resolution. So at the bottom, I have the data with coarsest resolution, and at the top, the data with a higher resolution. And I have 2 types of communication in this network. One is this convolutions, and then either going down through max pooling or going up with upsampling. But you can really see, for example, this line over here. This line is connecting with the full resolution data, feature maps at the beginning of the network and at the end of the network. This is what is called a skip connection, because it's a connection that is skipping part of the architecture over here, is skipping from the beginning directly to the end of the network. And this is what is called also a residual block, in such a way that we are exploiting feature maps from early in the neural network, where the feature maps are associated with simpler elements, and later in the neural network over here, when the feature maps are actually much more evolved, much more connected with more refined elements in our network. So when we are performing the last convolutions, as you can see here, I'm performing them on feature maps that are mixing some simple elements from the first layers and more complex elements from the last layers. Such a combination, when I apply my convolution through channels that are both mixing simpler and more complicated elements, is one of the strengths of U-nets, and why these architectures, which at the end are based on convolutions and on playing with the size of our data, that's why they're very widely used in computer vision, and you're going to see that they perform really well in the context of turbulence predictions as well. So an example of the level of predictions that we can actually get here. You can see an example here. We are predicting the U, V, and W fluctuations in 3D. So we're predicting 3-dimensional flow fields. We apply periodic padding. This is important because our flow is periodic in both the stringwise and spanwise directions. And the mean relative error is around 2%. So for both U, V, and W, I get relative errors of 2%, meaning that what we are developing here is a good surrogate of the original data and the original equations that were produced in the data. What I'm showing you here at the top is the DNS of instantaneous stringwise velocity fluctuations. This is a turbulent channel. On the first column, y plus 12, closer to the lower wall. On the second column, y plus 12, closer to the upper wall. So basically, we can show the dynamics in the near wall region on both walls. The second row gives us the predictions from the U-net, from our 3D convolutional network architecture, and the third row gives us the error. So as we can see, the patterns are in very good agreement. We can really see that both the streaks in the lower and the upper wall and the high and low speed regions are very, very well represented. Therefore, of course, if we use much more data, we will be able to reduce this 2% error even more. But in practice, this would be, at this point, diminishing returns because 2% error is really good. So we are, basically building a surrogate of our original equations through this deep learning architecture, which is basically able to integrate in time 5 viscous units. This is a schematic representation of the explainability algorithm. Again, more details are in this reference, so feel free to check it out. The idea is that I start with an instantaneous flow field. That's my input. Actually, I have three fluctuations, U, V, and W, but I will consider this as my instantaneous flow field. Then what I do is that in the first pass, I will use that instantaneous flow field to predict with my unit the predicted field. That predicted field will be compared with the real field, the one from the DNS, and I will get an error, basically an error function. Then I will start to remove extractors. And to remove extractors in practice, in this case, means to replace those regions with zero fluctuations. Because we are not working with instantaneous velocity values, we're working with instantaneous fluctuations. So to remove a extractor, to remove the volume corresponding to a particular Q event, is equivalent to replacing that volume with zero fluctuations. So when I eliminate that extractor, I apply my unit again, I get a new predicted field, which I can again compare with the simulated one, and I will get a different error function. In practice, at the end of the day, what I have is an importance score associated with each of those extractors, which is what we call the SAP values. So the SAP values give us a classification of the importance of each of these elements in the flow. And this, in principle, is a reasonably objective way to classify the importance, because these are telling us how relevant they are to make predictions and how they are contributing to the error of our neural network model. So how does this work? The first thing that we do is that we consider this G function over here. G is a linear model for the error between the neural network and the truth, okay, and the ground truth. So, of course, this linear error is going to be basically made up of a superposition of the contributions of all the extractors. So these binary variables Q prime I, these are 1 or 0. So 1 when the extractor is present, or 0 when the extractor is absent. And these phi values here, these weighting coefficients, these are the SHAP values or the importance scores. So G is a linear function made up of all the extractors that models the difference between the error between the neural network and the truth. Now, the true error, the true difference between the neural network and the ground truth is this f hat function over here. So what we want to do is formulate a mean square error minimization problem. So we want to really formulate it like this. I have the difference f hat minus g square. This I want to minimize. And what I will do is basically optimize the values of phi, which are minimizing this difference. So this optimization problem based on least squares is basically going to give me the phi values for each of these extractors in such a way that this f minus g square is minimized. Now, here there is one assumption, and it's this linearity. Is a linear superposition of all those extractors sufficient to be able to reproduce the error of something that is complex and nonlinear and potentially chaotic? Well, this f minus g square takes values of 10 to the minus 7. So in practice, even if this is a linear approximation to the error, we have so many extractors, and we have, to give you an idea, on the order of 150 to 200 extractors per field. So that gives you an idea of how many extractors we actually have. And the point is that these extractors are actually contributing to the error in such a way that we have so many that even if this is a linear approximation, this difference is actually close to 0. The second thing is how those extractors are being removed to calculate the error. And that's basically encapsulated in this pi x over here. This pi x is a kernel which is deciding which extractors are being removed when calculating these phi values, these SHAP values. And these extractors are removed in the so-called coalitions. One coalition is a group of extractors. In one field, we have 150 to 200 extractors, which means that if we look at all the possible combinations of extractors, all the possible coalitions, we will have 150 factorial to 200 factorial. So these are massive numbers, right? This would be completely unfeasible from a computational point of view to go through all these combinations and really try to eliminate extractors and see how things behave. However, what is done in practice in computer vision, and this is the method that we're exploiting here, is to choose a subset of those coalitions. Typically something that ranges on the order of 3,000 coalitions per flow field. So with those 3,000 flow fields, we get a significant representation of the possibly true set of sub-values. And the way that those are decided is with this kernel over here. In practice, each structure is present on a number of coalitions, which means that what we're actually doing is analyzing those structures in the context of other structures where we are actually working together. So all the complex, chaotic, nonlinear interactions of the flow, to some extent, they are captured by those coalitions, by the fact that we don't remove the structures just once, but many times in different coalitions, in different combinations of wall-attached, wall-detached configurations, such that we can really assess their role truly in a number of scenarios in the flow. Okay, so those two assumptions, the fact that we remove structures individually, that's kind of alleviated by the fact that we consider many coalitions, and the fact that this is a linear approximation is alleviated by the fact that we have so many structures that at the end of the day, the difference between the true error and the linear approximation to the error is very, very small. Now, results. What we see is that 60% of the structures are sweeps or ejections. If we remember a bit of quadrant analysis, what we know is that Q1s are outward interactions, Q3 are inward interactions. They're not really dominant. From wall-bounded turbulence, what we know is that Q2s, which are structures with negative streamwise velocity and positive wall normal velocity, those are ejections. And Q4s, or sweeps, which have positive stringwise, negative wall normal velocity, those are the dominant events. So in wall-bounded turbulence, Q2s and Q4s are dominant, ejections and sweeps. This is basically what we find in our analysis. 97% of the SHAP is from ejections and sweeps. That's an important thing to keep in mind. In fact, the ejections are very dominant with respect to the sweeps. This is expected at low Reynolds numbers. At high Reynolds numbers, they are more balanced, the distribution of sweeps and ejection importances. In fact, if we look at the importance per unit volume, ejections and sweeps have almost the same importance. So at these low Reynolds numbers, the ejections are very large, they're very important, but when we scale things with volume, the importance per unit volume of both sweeps and ejections becomes quite similar. Here what I'm representing in the vertical axis is the absolute value of the SHAP value of the importance. I'm plotting the absolute value because we want to see the effect of the structure, both if it increases or reduces the error. So in other words, the absolute contribution from the structure to the error. And I'm representing the structure importance as a function of the volume of the structure. And of course, what you can see is that there is a good positive correlation. So naturally, the larger structures are more important to the flow because I'm removing a bigger chunk of the flow and that will have a bigger impact on our flow dynamics. However, if I scale this quantity per unit volume, so in the vertical axis I'm showing you the SHAP per unit volume, and in the horizontal axis the volume of the structure, that correlation is gone. The larger structures in this red region are still present, and these are large-scale ejections. They're so large that their importance per unit volume is actually reduced. The most important structures in this cyan region over here are in fact medium-sized ejections. So ejections that are actually smaller, and therefore their importance is still quite prominent, and they become the most relevant per unit volume. And then in green I have here a wide range of structures with a small size and a range of importances, not too important, but perhaps not having the lowest importance either. And this range of importance per unit volume is what basically includes most of the structures in our flow. Okay? So when I look at things per unit volume, the most important structures are actually the medium-sized ejections. So now we have been looking at ways of defining importance. And what we do is that we try to find an objective way to define importance by looking at this surrogate of the equations obtained through deep learning and looking at what are the elements that have the highest impact on that error. That's in principle an objective way of defining the importance. But one could actually look at the Reynolds shear stress contribution of those structures. At the end of the day, these are Q events, these are regions of intense Reynolds shear stress, and we could actually look at the structures with the highest Reynolds shear stress to assess their importance. And in this figure over here, I'm plotting in the vertical axis the importance, and in the horizontal axis the Reynolds shear stress of those structures. And in principle, there is a pretty good correlation, right? So the more important structures also have higher Reynolds shear stress. What is interesting is when I represent the importance per unit volume in the vertical axis versus the Reynolds shear stress per unit volume in the horizontal axis. That's where things change. And then in this A region over here, what I see is a big spread. So suddenly there is not such a good correlation between the more important structures and the Reynolds shear stress of those structures. In region B over here, what we see is the structures with the highest Reynolds shear stress, and you can actually see that they are not necessarily the most important structures. The most important structures in this C region at the top are the ones with the highest SHAP per unit volume. So in fact, which are also mostly medium-sized ejections with some sweeps and even some inward interactions, but it's mostly ejections. In fact, the structures with the highest Reynolds shear stress are not the ones with the highest importance per unit volume. And that's interesting because at the end, the Reynolds shear stress is to some extent a physical argument, an intuition of importance, but the biggest importance is not necessarily that. The importance, we define it in an objective manner as the effect of the structures on the predictions in our surrogate model of our equations. So this is just to give an idea that not necessarily the Q events focusing on the Reynolds shear stress are the most important structures, but perhaps the one which have this higher SHAP value per unit volume are the ones that we should focus on. And of course, so far we have been looking at Q events and we classify the importance of those Q events. That's interesting, but our next steps, which we are highlighting here, have to do with identifying completely new structures. So what we are doing now is using the SHAP framework to locate regions of high SHAP and see what are the physical characteristics of those structures, how do they connect with Q events, how do they connect with vortex clusters, and what are basically the next steps to be taken here. So just to give some summary, what we do is that we try to use the SHAP framework, basically an explainable deep learning approach to define importance in turbulent flows and to really use this as a way to assess what are the most important regions in our flow configuration. I would like to again show the GitHub of our group. The methodologies that I mentioned today are not here yet, but they will be there as soon as the paper is published. All the other videos and all the other methods have their material here, so feel free to reach out to get codes, data, and also repositories of deep learning formulations and libraries. And once again, I would like to thank everybody who made this video possible, including InfraVis and the KTH Visualization Studio. This is also research funded by the ERC, the European Research Council, and I'll be very happy to keep discussing with you and telling you more about our research in future videos. Have a good day.